So, good afternoon, everyone. I hope you all are doing well, and welcome to today's session on on-device AI with Gemma 3N and PaliGemma 2, organized by GDG Visit in collaboration with CodeSil++. Thank you all for taking out your precious time to joining us with today. Before we begin, just a quick context. AI today is not just about cloud based models anymore. We are moving towards on device intelligence, where models run directly in your browser or on edge devices, and it enables faster and private and more efficient applications. That's exactly what today's session is focused on. And it's my pleasure to introduce to our speaker of the session, Nitin Tiwari. We are excited to have Nitin sir with us today. He is the Google developer expert in machine learning and currently works as a lead data scientist at Zeller. He has over 4 year plus experience in AI, ML, and computer vision. He has been building and deploying real world AI systems that go far beyond demos. Well, in today's session, Nitin sir will walk us through what vision language models really are, how Gemma 3 and PaliGemma 2 work under the hood, and we'll have some live and hands-on demo sessions showing on browser interface for tasks like image captioning and object detection and OCR. So, without the further delay, let's dive in right now. Over to you, Nitin sir.
Thank you so much for the introduction. Hi everyone. How are you? All good?
Yes, yes, sir.
So just to set some context about what we are going to discuss in the next 1 hour, okay? I want to keep this session a two-way conversational, okay? So it's not like I'm speaking and you'll be listening. So I want you to take everything that we can in the next 1 or 1.5 hours, right? And if you have any queries or questions, so feel free to put in the chat. So if I were in your place, I would have maxed every bit of this session. So feel free to put out your expressions or thoughts in the chat, and let's begin. Can I get a quick hand raise who are from the first years? Second years? Okay, a couple of folks. What about third years? So before we actually begin, I just wanted to get some understanding from your side. So have you been using Gemini, Chat GPT, or GPT models, Llama models? So probably for solving your assignments as well, right? So have you been using these models lately? Yes, no? Okay. I'm not audible to Kashfi, so probably just check your system. Hopefully I'm audible to rest of your folks, right? So have you heard about the Gemma models? Gemini is okay. I mean, everyone knows about Gemini these days, if I'm not wrong. But have you heard about what are Gemma models, or open models? All right. So today we'll be talking about Gemma, which is an open alternative. I won't call it as open source. There is a difference between being open source and being an open model. So let's get everything correct today. Whatever understanding you might have about these models. Okay. So we'll decode every small bit of information that we usually don't get on the internet as well sometimes. And I think this is a great way to get some doubts clarified as well. So today I'll be speaking about the vision language models, the open vision language models in the Gemma family, which is called as the PaliGemma or PaliGemma 2 models, along with the Gemma 3N. Okay, so let's quickly begin. So just to share a more, about myself, I'm a lead data scientist at Zellar. It's a platinum Google partner. So we work with Google on a lot of projects. Many of the top fashion and garment companies are our business partners and clients. I've been a Google dev expert in machine learning from the last 3.5 or 4 years. and I've been a key contributor to the Google Dev Library, which was an open source project started by Google, where developers across different domains like ML, cloud, Android can contribute to some of the projects. I don't know if you have heard about TensorFlow, but it was when back then when it was a thing, I was a contributor to TensorFlow.js. So it's a JavaScript library for TensorFlow running models on browser, right, on device. And I've been a key contributor to Gemini and Gemma cookbooks as well. I've been advocating the Gemma models in the last 1.5 years. Apart from that, I've been a technical speaker and given talks across different parts of the world, and I love writing blogs on AI and ML. So feel free to check out some of my work. But let's get focused on what we'll be covering today. So I'll be briefly speaking about what is vision language model. Okay, what are these VLMs? How do we use that? What is the significance? Then I'll be talking about architecture of a typical VLM. So I'm sure like many of us use Gemini, Gemma, and all these models, but the thing is we only call APIs. So through this session, I just wanted to take your understanding beyond just calling APIs. So whenever we work on these models, so it's as a developer, right? It's our responsibility to also understand how these models fundamentally work. So I'll be decoding what does a typical VLM look like. Okay, so let's say if someone asks you, can you explain the architecture of a VLM? I'm not expecting you to know every bit of how these VLMs work, but a basic understanding of VLMs. I'll be speaking about Google's open VLMs, which is PaliGemma, PaliGemma 2, and vision language models like Gemma 3 as well, right? I don't know if you have heard about Matryoshka transformer or even the word Matryoshka, but I'll be covering that thing. So very interesting concept. And then finally, at the fag end of the session, I'll be doing like hands-on. So we'll be doing hands-on with inferencing PaliGemma 2 on the browser. Second years, I'm not sure about you folks, but most of us have used Google Colab, right? So the reason behind not using Google Colab and using on-device approaches, I just wanted to take your understanding to that level that these models can be run on device as well. So you don't have to connect to an API and send out your data to the cloud. You can also do something right on your machine and right on your mobile phones as well. And if the session interests you, if you want to learn more about how these models work, how do you deploy these models, how do you fine-tune these models, I've got some resources for you as well at the end. So let's begin. Before we start, can someone like put in the chat for me what is VLM, vision language models? I'm sure many of us have heard about LLMs, right? Large language models. So I'll stop my presentation for some time. Can someone put in the chat like what is VLM? I think the name itself suggests everything. So folks, I'm expecting like it's two-way communication happening. So it's a good opportunity for you as well if you have any queries or anything in your mind. So let's get that clarified. So someone says image to text models that can understand images too. Yes, of course, visual models. Perfect. Yeah. So spot on. VLMs can also understand images along with text. And just to give a brief introduction about VLM. So these are multimodal. Multimodal, as the name suggests, it can take input images, not in images, but any kind of data in different modalities like text or images as well. And in return, it can generate text output as well as image outputs. So these are VLMs and they excel in zero-shot capabilities. So when I say zero-shot, right? So zero-shot is something when you don't need to train the model anymore. It's capable enough, it's intelligent enough to understand what is the requirement, and then it generates output given query. So I'll explain what is zero shot with an example. Okay, and then these models can also capture some very sophisticated and complex properties like spatial properties. So if you want to identify where exactly the object lies in an image, right? So that's essentially object detection and classification and segmentation as well. So these models are good enough in working in those aspects as well. If you have been following or practicing ML for a while, long before the Gen AI era came into the picture, right? So before that, we used to have some traditional ML models. So in this example that you see, In the middle there is an image. At the left hand side there are certain use cases. Let's call it as use case for the sake of simplicity, right? So with the same model, with a single model, you can do all these things. You can do object detection, you can do segmentation, you can do OCR, as well as image captioning. So when I talk about the era, before the Gen AI era, right? So talking about 2017, 2018, and so on, we used to have libraries like TensorFlow. We still have it. Then PyTorch, and you must have heard about YOLO models as well. YOLO only ones. So these models were specially trained for tasks like object detection and segmentation. So every given task, you would require to train a new model. Okay. And the thing was, these models were pre-trained. So if you want to create a custom model of your own choice, right, by adding more layers or by adding more classes, so you explicitly had to do some kind of training or fine tuning, which we also call it as transfer learning. So no more doing transfer learning on all these models. Just a single model is capable enough in doing all these tasks. Whether you want to do object detection, it can do that for you. Segmentation, as you can see, it can pixelate or mask every pixel belonging to a particular class, which you see at the right hand side. It can do OCR, optical character recognition. So if you want to extract text from the, it can do that for you, and then image captioning as well. So VLMs are capable enough in doing all these tasks, and all this is zero shot. So you don't really have to train the model to detect a new class unless it's a very complicated object in the image. Now let's talk about the architecture of a typical VLM, and the word typical is important here because different companies like Google and Meta and Microsoft and every other AI company is following a novel architecture of their own, right? But any typical VLM will look like this. Okay, so we start from the bottom. I'll just simplify this for you so that it's easily understandable. So since we are talking about VLM, it's vision. So we start with the image. Okay, we pass it to an image encoder. Image encoder is nothing but a model itself. Okay, so it can be a clip model. Clip stands for contrastive language pre-trained model. It was a model which was developed by OpenAI, and surprisingly, it's open source model. Since OpenAI is known for not, developing open models, right? But this is open source and easy. It's available on Hugging Face and their GitHub repository as well. So CLIP is contrastive language image pre-training. Just remember the name for now. I'll explain what is the use of this. So the image encoder can be a CLIP, it can be a SIGLIP, it can be MobileNet V5 or any other model. I'm sure you must have heard about MobileNet as well. So these are the deep neural networks for specifically trained for on-device use cases. Okay, so once we pass the image to an image encoder, we get some kind of embeddings, okay, or some tokens, which you can see here. Okay, so if I zoom in this part, this 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 particular thing, if I zoom this in, so once the image encoder output goes to the multimodal projector, this is what we get. Okay, so the red ones are the visual tokens or embeddings of the image. The yellow ones are the text prompts embedding tokens. Okay, so text prompt can be, for example, if I go back, this was my image. Okay, and let's say my text prompt was, can you do OCR on this image? So ideally my output would be a portrait of experts machine learning. Or let's say if my prompt was, can you do some image captioning on this? So my output would be a portrait of a man in blue shirt and so on. Okay, so yellow one was my nothing but can you do image captioning? So that was the thing, and machines don't understand any kind of languages. So at the end, these are nothing but embeddings and tokens. Okay, so yellow is nothing but the text prompts embeddings, and the red one is nothing but the image embeddings. Both of these are concatenated. The plus sign that you see, this is not addition. This is not a numerical addition. This is concatenation. Okay, these are concatenated and then passed to a text decoder model. So you pay attention here. There are two models we are talking about in a particular VLM. One would be the image encoder, which will be encoding or which will be creating embeddings of the images. And these can be like CLIP model. CLIP is contrastive language image pre-training. SIGLIP is a modified version of CLIP, which was developed by Google. So SIG stands for sigmoid. sigmoid loss for language image pre-training. Okay. Uh, and then finally we have the text decoder. So text decoder is nothing but the language model we are using. So this is the V part, and this is the L part of the VLM. Okay. To give some more example and context, to simplify this understanding of the architecture. So long before you asking questions about your assignments on Gemini or ChatGPT, right? I'm sure like you receive PDFs of assignments on your class group, and then you don't invest your time in understanding what is the question, and then you simply upload it on ChatGPT or Gemini and get your answers. And then you make some tweaks so that it doesn't look like it's AI generated. But how do these models even work in the background? So, while training these models, most of these models are trained on open source data like Wikipedia. And if you go to Wikipedia, I don't know if people still go to Wikipedia to find any information, but still, it's a rich source of information. So if you go to Wikipedia for any, given article, you'll see some images and the respective captions. So this is how the model was trained, by scraping the Wikipedia and lots of open source data. And for every image that you see on Wikipedia, right, there is an image and there is a corresponding caption for that. So let's assume we have hundreds and millions of images and the respective captions. So the first image that you see on the stack, it's an image of a dog sitting on a bench, and this is the respective caption. Below that, there will be some image like, some cricketer or something of that sort, something random, and then the respective caption and so on. Now, if we encode all these images and if we encode all these texts, okay, so coming back to the simple mathematics that we learned in standard 11, so you know what is scalar, you know what is vector and matrix, right? So this is a vector, okay, and this is also a vector. If we do a multiplication between the two, we get a matrix. So I1 T1 is I1 T1 here, then I1 T2 would be I1 T2 and so on. The diagonal elements that you see, right, so this is nothing but an image of a dog and the caption, a dog sitting on a bench. I1 T2 would be an image of a dog and something else, the second caption or the second text in the data set. So let's assume, it was a caption of, let's say some place, okay, Taj Hotel or something of that sort, for example, just a random thought. So do you think the image of a dog resembles with a text caption of a hotel or, something of that sort? No, right? That doesn't make any sense. And then let's say I2 T1 is nothing but the second image in the stack, okay? For example, some famous personality, and then the T1 is a dog sitting on a bench. So even that doesn't make any sense, right? So the idea here is proper captioning should be done with respect to the given corresponding image, which can be only achieved if you take a look at the diagonal elements. Okay, so I1 T1, I2 T2, I3 T3 until IN Tn would be your elements that you need to maximize. Okay, so the loss function will be minimized in this case. So that's how this contrastive language image pre-training works. It takes into account both the models, the image encoder and the text decoder. Okay, it should be text decoder, not encoder. So that is what CLIP stands for, language and image. You are training both the models simultaneously. Now there is another, if I go back to the previous slides, CLIP is this. There is another model called as SIGLIP. It's an improved version of CLIP. Okay. The only difference is, let's say I have two objects in my hand. Okay, this is a mobile phone and this is, let's say, a mouse. So as a person, what do you think? What is the probability of this being a mobile phone? I'm not seeing the chat, but I'm sure that everyone knows this is a mobile phone if we see it visually. But if we ask the same question to a computer or a machine, it doesn't have that sense that we have as humans. So it will say that, okay, this is 99% of mobile phone, but still there is 1% of chance that this is also a mobile phone. Okay. So when we say this, the probability is distributed. So 0.99 and 0.1. So if there is a more complicated object which looks similar to a mobile phone, it would be 50 or 50 and something like that. So instead of having a probability output, okay, that is also called as softmax. So if you have heard about this, softmax is nothing but it gives you probabilistic output between 0 and 1. 1 is nothing but maximum output, okay, maximum accuracy. 0 tends towards like the accuracy is very poor. Something between 0 and 1 is nothing but, if it is 50%, then that is the 50% of your, if it is 0.5, then that is 50% correct as predicted by the model. But Siglip, what it does is, Siglip only works in binary. It can either be 0 or 1. So if I'm saying this is a mobile phone, yes, this is a mobile phone. This is not a mobile phone. That is for sure. So I don't have to maintain, the probability of each and every object in the image. That is how Siglip works on a very broader level. It's not that easy. Okay, it's quite complicated if we read the paper which is available. But just to clarify things in a simplistic manner, this is how the Siglip model is different from Clip, and it significantly improves the accuracy of these VLMs when we use Siglip over Clip. The reason behind that is I don't have to maintain different memory for each and every object or each and every classes belonging to that particular image, right? I just talk in terms of zeros and ones, and that's how the accuracy is also increased. So this is how VLM looks like. Okay. So I1, T1, I2, T2, I3, T3, all these will have values 1. It's just an identity matrix, you can call it as, and the rest of the elements will be 0 in my entire matrix if I use the Siglip approach. So let's talk about vision language models which were released by Google. So Gemma started back in Feb 2024. It was a text only model, so text input and text output. I'm talking about Feb 2024. Before that, in December 2023, Google came up with the Gemini era. So the first version of the Gemini model was released. But I'm not sure if you remember, before Gemini, there was something called as Bard. So Bard was the product, and the underlying language model which was used was Pathways language model, also called as the PALM model. So if you go to Google and search about it, right? So PALM was Pathways language model, which they deprecated, and then the Gemini era started. Okay, it's decommissioned. So until Feb, from Feb to May 2024, there was only text input, text output models, and then during Google I/O 2024, Google announced the PaliGemma, the very first vision language model, okay, which was open. Why I'm saying open is because Gemini had already those vision capabilities. It could understand PDFs, it could understand images, videos, and so on. But PaliGemma was the very first model which was open. There is a difference between open source and open model. Okay, open source is something that you can alter as a developer. So these models are, the model weights are openly available on the GitHub repositories, and if you are able to tweak those original model weights, that's called as open source model. But if you can take those model weights as a reference and fine tune it, then that is called as open models. Okay, so the LLM backbone which was used for PaliGemma was the Gemma 1 model with 2 billion parameters, and vision encoder was Siglip, the one that I just explained. Together, the model size was 3 billion parameters. So you can, count, since it was a 3 billion parameters model, 2 billions was occupied by the Gemma language decoder. So the Siglip size was 1 billion parameters. You can, roughly estimate. Input modalities, it could support both text and images. Key architecture was connector and a decoder, and it was best known for image captioning, object detection, and segmentation. This was the very first version released. Then in the month of December 2024, they came up with PaliGemma 2. The difference was they used the Gemma 2 model instead of Gemma 1 as the language model, but the vision encoder remained the same. So that means if I go back, they only changed this part, the text decoder. So this was still using Siglip. Okay. And one more thing, the gray ones that you see, right? So you cannot change this. It's frozen. It's not trainable. You can only train this, the not frozen part. Another thing was it was available in 3 different parameter sizes. So 3 billion was the smallest. Then the 10 billion parameter was a medium-sized model. Okay, so good use cases for on-device, where the accuracy mattered the most. Okay, and 28 billion was the highest in size. Okay, so when the accuracy mattered most over the size, so it's okay even if I don't run it on device, I want the accuracy to be best. So that's where 28 billion was used. Okay, and again, if you subtract one from each, you will see that the Gemma 2 models had 2 billions, 9 billions, and 27 billions parameter in sizes. So that's how PaliGemma 2 was built. Then in the month of Feb 2025, they came up with PaliGemma 2 Mix. So Mix was nothing but a fine-tuned version of PaliGemma 2. So when I say fine-tuned, right, the model weights can be pre-trained or it can be fine-tuned. Mix a combination of both. So if you want to train the model, or if you want to inference on something which has more use cases, right? For example, image captioning, you can do long and short captioning as well. So when I was trying this PaliGemma 2, right, captioning was not good enough. It was giving some very short answers about a particular image. It was not going into the details. So I'll show some examples so that it becomes clear to you. Object detection, it was still doing object detection, segmentation as well. OCR, in terms of OCR, it was performing well as compared to PaliGemma 2. I'm talking about the Mix model. And then it was also able to do the long captioning. Then in the month of March 2025, they came up with Gemma 3. So they moved ahead from the Gemma models, or the PaliGemma models as well. Okay, so the language decoder or the LLM backbone itself was Gemma 3. So it's a native model in itself. Okay, and they were using a custom built Siglip version of this. So they were still using Siglip as the base image encoder. Okay, but the architecture was a bit customized based on certain needs that they had. And it was available in 3 different parameters again: 4 billions, 12 billions, and 27 billion parameters. Amazing part of this was it also started supporting videos and audios along with text and images. And it was a decoder only key architecture, if I talk about the architecture of this model. Best known for native multimodal tasks. Okay, so if you have multimodality, let's say if you want to inference both audio as well as video or images in the same API call, you can do that as well. So that was the beauty of Gemma 3. It was announced in March 2025. Then during Google I/O 2025, in the month of May, they announced Gemma 3 N. So N was supposedly meaning Gemma 3 Nano, but you won't find an official official name of Gemma 3 Nano anywhere on the internet, but probably it means Gemma 3 Nano model only. And the vision encoder, they moved from Siglip architecture to MobileNet v5. Why MobileNet v5 was? Because these can also run on device on mobile phones. Now, if you see the parameter sizes, it was available in E2B and E4B. I'll explain the meaning of E here. Okay, as you can see, in none of these models you will see the E word, right, or the E letter. So E stands for effective parameters. So what is effective and what is the difference as compared to any other model? I'll explain subsequently in the next slides. Multimodalities, yes, it could still support text, images, audios, and videos, and it was based on the Matryoshka architecture, which I'll be explaining you. What does a Matryoshka architecture pertains to? Okay, and it was best known for on-device multimodality tasks. And in the month of July 2025, they came up with PaliGemma. So it was again similar to any other Gemma models, vision language models, but it used Siglip as the vision encoder. So they even trained the vision encoder in this case. If I go back, so this part, the gray part, they had trained the Siglip model specifically on medical data sets. Okay, and then they released the model weights on Hugging Face as well. So if you go to Hugging Face, you type Siglip. So this model is available here. Okay, you can just read about what this model does and how it was trained. So it's a variant of sigmoid laws for language image pre-training, Siglip. Yeah. specifically trained for medical images, and it supports 448 cross 448 resolutions. So that's why you see 448 here in the name as well. Okay, so today we'll be talking about the blue and the yellow thing here on this slide, PaliGemma 2 mix and Gemma 3N. We'll be doing hands-on with PaliGemma 2. Okay, so let's talk more about PaliGemma 2. So it's an enhanced version of PaliGemma, but uses the same vision encoder like Siglip, as I explained in the previous slide, with Gemma 2 as the backbone. So PaliGemma 2 is available in two different variants. One is the PT, which is also called as the pre-trained version, okay, used for a variety of tasks. And the FT version is nothing but the fine-tuned version, which is specifically trained on some research data sets, just like the Siglip one or the Gemma one. And it's available in 3 different resolutions and 3 different parameter sizes as well. So a very vague explanation would be Siglip says I'll handle the vision capabilities, and Gemma 2 to be the text decoder model says I'll handle the text part. That's how the PaliGemma 2 model works. Okay, and just to give you some gist about what this can do. So PaliGemma 2 mix, it was a tuned version of both PT and FT versions, right? Built for common use cases like object detection, segmentation, both short and long captioning, and visual question answering. So it can do everything zero shot. You don't have to explicitly train the model for all these tasks. The official support from Google for these frameworks includes Hugging Face transformers. So you can do inferencing on the PaliGemma 2 mix model using Hugging Face transformers. If this thing is new for you, I would encourage you to check about what is Hugging Face, what is the transformers library, what is Keras and PyTorch, right? And these are the backends. So Keras is a backend, and similar to that, PyTorch and JAX are also some backends that you can use. Okay. Open source contribution. So there was no support for Onyx. Onyx is nothing but Open Neural Network Exchange. So what is Onyx first of all? Onyx is, let's say Google builds a model. Let's call it as, PaliGemma or any other model. Let's talk about open models only. We'll not talk about any proprietary models like Gemini. So let's say Google builds some model. So they have their own recipe and architecture to, develop or train these models. And they won't share it with any other company, right? Because it's their property. But what if I want to use it in an ecosystem that uses Meta in the backend, okay, that uses Facebook's architecture? So this is where Open Neural Network Exchange comes, where you can, convert one model's architecture into another without changing the weights of the model. Okay, so that's how Onyx works, and I contributed to this as an open source project, which we'll be doing today hands-on. Okay, so we'll be running a PaliGemma 2 model. It's not the original model weight. Okay, it's not the original PaliGemma 2 model, but the Onyx conversion of the original weights. So we are still using the original weights, but in a format which can be understood by the transformers.js library, so that these models can run on browsers as well. The thing is, if I go back, right? If I go back, so these models are trained to work in Python programming language only. So if you go to any model on Hugging Face, right? If I go here, so you'll see the boilerplate code that they have given. Everything is in Python only. So let's say we want to run the same thing using JavaScript. So there is no support given for these models. So that's where Onyx comes into the picture. So you can convert these models so that it's platform and language independent. Now let's talk about Gemma 3. So again, it's an open multimodal model design for on-device AI use cases. So there's a difference between Gemma 3 and Gemma 3N. When you want to run models on device, and you want to do those inferencing on mobile phones or any small devices which don't have that GPU capabilities, that's where Gemma 3N is preferred. Okay, it uses MobileNet V5 as the vision encoder for lightweight visual processing. So using a Siglip model would be quite expensive. Okay, if I use the Siglip encoder, right, it would be quite expensive over using MobileNet V5. So that's where they made those architectural changes. And then I was talking about the E thing, right? So E is nothing but effective parameters. So what is effective here? These models were originally 5 billions and 8 billion parameters in size, but when you run this on device, right, these models adjust themselves with respect to the constraints, with respect to the hardware capabilities that you have, so that you don't face any issues while inferencing on smaller devices. So even though the original model was 5 billion parameters, it adjusts itself so that it can be as compact as 2 billions and 4 billions as well. So that's why we call it as effective. And the capability of adjusting itself in different environments, that's where the mad former architecture comes into the picture. Okay, so of course it supports multi-modalities like text, images, audios, and videos. And mad former is matryoshka transformer. I'm sure many of us have heard about the transformers architecture. Okay, attention is all you need, the paper that laid the foundation of all these language models that we see today. So matryoshka transformer is nothing but a customized transformer version which uses the matryoshka approach, and it selectively activates the subsets of the model parameters. So that's where this E comes into the picture. So if I don't want to use the entire 5 billions, right? If I don't want to use the entire 8 billions, I can activate only a few portion of the model without negating on the output. So I'll still get the same output that I was expecting without drop in the accuracy. And then it also includes PLE caching. So PLE caching is nothing but per layer embedding caching, which allows the embeddings to be stored fast and locally, right? So whatever embeddings we were seeing in the previous slides, right? The image encoder was getting some image embeddings, the text decoder was getting some textual embeddings. So these embeddings are stored as cache on your mobile phones. So with that thing, you don't have to create new embeddings every time for similar objects or similar images. So this is how it has been made possible to run all these models on these small devices. This is an example of mobile vision LM. Again, this is an open source project that I was working on and released back in May 2025. So the example that you're seeing is not Gemma 3N. It's similar to that. So coincidentally, Gemma 3N was also released on the same time during the same duration of Google I/O 2025. But the example that you see, it's a custom vision language model which uses Siglip as the vision encoder and Phi2 as the language decoder. So Phi2 is the sorry, Phi2 is nothing but the language model by Microsoft. Okay, it's a very compact model with 2.7 billion parameters, and as you can see, the size, it's small enough to run on a mobile device as well. So you can check the GitHub repository for this particular model if you are interested in learning how the model weights were converted and quantized. Quantization is another, uh, you know, what do you say, a technique where you can reduce the size of the model weights. Okay. So let's say you are working with floating point numbers 1.2 or 1.5. If you convert it into an integer, 1.2 will become 1 and 1.5 can become 1 or 2, for example, if you round it up. So that way we are slightly compromising on the accuracy, but the size decreases drastically. So that's where quantization comes into the picture. So the Q4F16 that you see, it's a float 16 point, float 16 number, which is converted to Q4, and then the model weights are bundled and deployed on Android as well. So you can check out the GitHub repository if you are interested in learning how do you do this from scratch. And it was done using MLC, which is machine learning compilation. It's a framework where you can convert all these open models into a specific format which can be run on device. It's similar to Onyx, but they have this is a framework that this community has come up with its own. Okay. Uh, just give me a minute. Yeah. So we were talking about Matryoshka transformer, and I hope you have seen these dolls, right? So Matryoshka is nothing but it's a doll, Russian doll. It's a toy where within a doll you'll find another doll. Okay. So think of this each doll as a model. Okay, the bigger one being the bigger model, and each subsequent models are the models of smaller sizes. And so if you notice this image, okay, so the model parameters are in a way, where a submodel can be used without it being the need of using the bigger model. So that's why we were, saying that it can effectively use 2 billion or 4 billion parameter models instead of using a 5 billion or 8 billion parameters. So it activates only the required subset of parameters based on the request that you are sending. Okay. So if you're, sending some similar prompts, can you caption this image or can you do the OCR? So it will save all those kind of embeddings that you are sending, the textual embeddings or the image embeddings. And based on the requirement, it will self-adjust and do the inferencing. So you no longer have to manually choose whether it's 4 billion or 3 billion or 1.5 billion in size, right? It can auto scale and auto adjust. And each of these models are independent of the other models when the resources are limited. So if I want to run something, on a bigger image, I would prefer this model. If the task is less complicated, I will prefer a smaller model, right? And between E2B and E5 and 5B, okay, you can create any custom model of your own choice. So you can also come up with something like 3.7 billion parameters or 4.3 billion parameters, right? So that's the beauty of this architecture. You can, self-adjust this based on your own needs and comforts. Today we'll not be talking much about Gemma 3N when it comes to hands-on, okay? But I would encourage you guys to check out the architecture of what Gemma 3N looks like, okay? What does the Matryoshka transform architecture looks like? Okay, so if you go to the official documentation of Gemma 3N, so it explains every bit about how this small model works, right? There is another guide that Google has published. It's a collab notebook where you can also slice and create our own custom smaller models using this Matformer architecture. So this is out of the session. It's not in the content, okay? But just for your information, you can check this out, and you can also read the paper if you're interested more in understanding how this model works, right? So let's get started with the hands-on lab of PaliGemma 2 on browser. I hope everyone has followed the manual which was shared earlier with the prerequisites so that we save up on time today in the session. This is another, again, open source project that I built, and I just wanted to share it with everyone here. So I just keep sharing things with the community, so it reaches a larger audience. So how we come up with a version of PaliGemma 2 which could be inferenced on the browser. This is how it looks like. So as I said, every vision language model will have a vision encoder and a language decoder. In this case, it was Siglip, and Gemma 2 was the language decoder. Okay, and every vision encoder, if you drill this down further, every vision encoder will have a vision tower and a multimodal projector. I'll not go into the details of what does a vision tower does, but its task is to extract some features, right? So if you have heard about CNNs, how do the CNN model works, right? Convolutional neural networks. These models are specifically trained for image classification or image or vision related tasks. So it will extract some key features, right? Like what is the shape, what is the size, what is the color being used, and so on. So it extracts all those details, and the multimodal projector, it will project all those tokens, visual tokens, through Onyx, Open Neural Network Exchange. It's an open source library used for conversion of models from one format to another. We created a file called as vision_encoder.onyx. Similarly, we did this for the language decoder. So the Gemma 2 model had attention layers, the decoder layer, and the positional embeddings. Positional embeddings, I can explain you quickly. So, for example, uh, for the phrase or for the sentence, I love dogs. Okay, so I is a token, love is a token, dogs is a token. What if I use the same tokens but in different orders? So I dog love. Does that make any sense? No. We are still using the same embeddings, but now since the position has been changed, it doesn't make any sense to me. I dog love makes no sense. So that's where the positional embeddings comes into the picture. Okay, so it retains those positional aspects of the embeddings which were encoded, right? So that the model knows what output should be given. And for this layer as well, for this language, the entire red thing, we get a file called as decoder model merged.onx. And then there is this embedding layer as well. It's a separate layer for embedding tokens, for which we convert the whole embedding layer into another file called as embedding tokens.onx. Together we quantize all these three these model files. Now this yellow thing, quantization, that you see, it's not mandatory, but it's ideally preferable when you want to run these models on device, which is the whole point about this session. We are talking about running these models on device. So that's where quantization comes into the picture, right? So it can be floating point 16, it can be integer 8, it can be unsigned integer 8, q4, q4 f16, and this is bits and bytes 4. Okay, I'll not explain everything here right now, but the overall task of this particular layer or step in this whole architecture is it will reduce the size of the model without much degradation in the accuracy. So after quantization, we'll get the final ONNX weights, which can be readily used in your application. So we'll be using this thing, this orange thing, for inferencing. I've already done the quantization and the conversion of the model weights. But if you're interested in learning how these conversion had happened, right, you can go to the GitHub repository. So here you'll find two notebooks. One is the conversion, and you can also check out the official GitHub repository of the Gemma cookbook, which the Google team maintains for different open source projects, right, by the community and by their own team as well. So you can also find the same thing here. If you go to demos, okay, so this explains every bit about how all these steps had been implemented. Okay, so right from installing on and different versions and different compatible libraries for conversion of the models, how do you set up the environment, how do you convert the vision encoder, and how do you convert the language decoder along with the embedding tokens. So if you're interested in more of doing things from scratch, you can just check out this notebook. Okay, thing is, it will not run on a free version of Colab, so you'll need at least a L4 GPU, at least an L4, and if you have a 100 GPU, then it will work the best, right? So once the conversion happens, how do you quantize these models using the script? Okay, so these are the parameters. You just pass in the whole input folder, and what modes of conversion do you want, whether it's FP16, whether it's integer 8, and so on. So if something is going above your head, just let me know in the chat. But I just wanted to highlight these small things which we don't often find in documentations and all. So it is more in research work and how do you do things from scratch. This would be the best notebook for you to get started with, and you can tweak this notebook for any other model as well. So if you want to convert Gemma 3 or Gemma 3n as well, with a little tweaks in the codes, you can also do it for other models, right? And once the model has been converted, you can find the final onyx weights, which is this orange one, right on this Hugging Face repository. Okay, so behind the scenes, it has generated these many, like 29 files to make the inferencing. And let's say if you don't have a good laptop or machine to do inferencing today, you can also do it on Google Colab. Okay, so the second notebook does that thing for you. So you can set up the environment. We'll be using Node.js because it's a JavaScript based, inferencing. We are not using Python anymore. So how do you prepare the prompts? When we see the prompts, there is a way of defining. So it starts with the image token. So it's a standard token used for PaliGemma 2 models. Okay, so this is how the model understands that the input is an image along with the text, and then finally you can concatenate or pass the text as well. So you can do object detection, you can do captioning. So a very interesting, story. So the PaliGemma 2 mix model was released in Feb. I was working on this project in December 2024. At that time, there was only PaliGemma 2. And the output we get right after conversion. It's not the original model weights anymore. It's the converted model. So somehow there is a very minute drop in the accuracy. And PaliGemma 2 model was not good enough in long captioning. It was just giving a very single one sentence response, like a dog is sitting on a bench. And the same thing when PaliGemma 2 mix was released. I was planning to publish this a day before, but then they released this model, so I had to change the model weights. I had to adapt it to the PaliGemma 2 mix models. Okay, so this is where you can choose the model ID as well. So the 3B mix 224 and 3B mix 448 was not in the list. And then when I did the inferencing on the very same image and very same prompt, I was able to get a very detailed response. So these are the small things that you learn, when you do things on your own, when you understand like how do these models work, right? So coming back to this is zero shot object detection I did with PaliGemma 1 back in June 2024. Okay, so the thing was, just to give you some idea, these models are trained for only images. Okay, so you cannot do inferencing directly on videos. But as you know, videos are nothing but it's a collection of frames. So this is zero shot. The only thing I provided in the prompt was detect person, phone, and bottle. So without explicitly training the model for these objects, it was able to detect all those objects. And then segmentation. Segmentation, as you can see the differences, it can segment or pixelate every single pixel belong to the relevant class, whether it's person, book, or mug, right? Idea behind this was, if you go back to Google's documentation, okay, the official documentation, it says that you'll need a separate library to decode the vision, the segmentation results. So can someone tell me how does a segmentation differs from detection when it comes to inferencing? I mean, of course, detection will have a bounding box with 4 coordinates. But what does segmentation have? It's not 4 coordinates anymore, right?
A collection of many coordinates.
Exactly, right? So if you say that, right, this is a person, and you will find like there will be 16 key points. So the PaliGemma 2 model, which was developed, right, it was trained in a way that it can identify 16 different key points that will create a boundary for that particular object. Okay. And this is how it works, right? I don't need to explain about detection, but segmentation is a bit complicated thing when it comes to decoding the output. So this is the image. This was a text prompt. I gave it to PaliGemma 2. The green one is nothing but the person. The blue one is nothing but the book. What PaliGemma 2 gives in responses, it will give the coordinates, okay, 100, 200, 300, 400, whatever it is. It's a random number I've given just for the sake of simplicity. There will be another token called as the seg, which stands for segmentation. So there will be 16 different segmentation points, which will be drawn on top of this. Detection is easy, so you can just normalize it. So let's say if it is 100, what I will do is 100 into size. Okay, so for different image sizes, I'll need to normalize it, right? I'll need to normalize it based on the image width and height. After that, I can get the 4 different coordinates. But segmentation points, decoding that was difficult because that's how they build this model. So there was this library called as Big Vision. So if you type Google Big Vision, right, it's a JAX or a flags based repository. That does a lot of tasks like evaluation and so on, okay, or projection. But specifically talking about PaliGemma and PaliGemma 2, so the segmentation points that you see, right, 64, 82, 400, sorry, not 400, but 64, 82, and so on. So you cannot directly use it as the X and Y coordinates. It has to be decoded somehow, which was being used with, Big Vision library. So you can check this out. Today's demo will not show segmentation because it is to, add another layer of Big Vision in the browser, but we'll be briefly, doing hands-on on OCR, image of captioning, object detection, and visual question answering. So let's get started. I'm sure you have already done the first 4 steps. I just wanted to save up some time for the 5th one. Okay. So if you have already done this, follow me along. If not, please follow the manual which was shared earlier. Okay. And let's begin. I've already set up the server in the backend so that we don't waste time on this. So if you're doing this for the very first time, it will take like 10 to 15 minutes depending upon your internet speed and so on to download the model weights. Okay, so we're downloading the model weights and the processor. And once it is downloaded, we can just go to localhost 3000 port number. So let me detect a face, for example. And just to show you this is an on-device thing happening, I'll also open my process. Okay, so let's see. So you can see the CPU is increasing, the occupancy of CPU and GPU. Okay, so this was the response from the model. It gave coordinates like 72, 418, 377, and 653, which I had to decode. Okay, so since this is a string, right, the first step was to convert this into an integer by using some simple regex techniques, right? You know what is regex, right? Regular expressions. And 72 cannot be directly used, so it has to be normalized by dividing with the image, width and height, and then finally using this as the label to draw the bounding box. So this is purely zero shot. So if I just also try detect Google logo, so you see nobody had trained this model for detecting a Google logo. So if you talk about traditional computer vision or object detection models like YOLO and efficient det, right? So these models, were pre-trained only on a particular set of classes, like common classes, like you must have heard about COCO dataset, right? Common objects in context, which includes person, bike, TV, laptop remotes, and so on. So Google logo is an example of zero shot detection. That's what it can do. Now without changing the model, I'm also giving a prompt, for example OCR on the same image. So experts machine learning, it is correct. Now the thing is, we are using a very simple image with clear distinctive text visible on the image, right, along with the person. Let's try something complex. I don't know, like, any suggestions?
Some monument or anything else.
Sorry, monument or ornament?
Monument.
Audio related.
Monument.
Okay, monuments. Okay. Let's see. So now my question is, I'm asking the model to identify the monument, and it's a visual question answering task. Not an object detection, not captioning, not OCR, but identifying the monument. And Tower of Pisa, yes, that's correct. I can also ask it to caption it. Now, the beauty of PaliGemma 2 model was it was trained on a wide variety of languages. So if you type caption followed by the language code, right? For English, it will be EN. If you want to do the same thing for Hindi, just type and then space HI. This happens because I need to add some checks in the code as well, which can be a good opportunity for you to explore and send in some pull request. Sometimes it doesn't take the same image. So what ideally I do is I just refresh the whole page and send the prompt. So you see the response, it's quite accurate. I won't say that it was able to identify, because the task itself was not visual question answering, it was a captioning kind of question. So which is pretty good. So based on the language, right, whether it's Hindi or English, it supports those kind of multilingual yeah, this as well. So that is this thing. And if you want to try something more, you can also try out segmentation. If you want to create a new feature, right, if you are interested in creating a pull request for that, feel free to understand how does this architecture works, how do you convert the segmentation thing into a thing which can be understood by transformers.js, and that feature can also be enabled into this whole application. So the idea behind this was to give you a gist of how these models can work on device, okay, without you needing to send any API request or API calls and sending out your data, right? uh, so that's all about the session. Some resources for you to get started. If you are new to the Gemma family models, if you want to learn more about vision language models, I would suggest don't jump directly to the latest models. First, start with the basic ones, which is PaliGemma 1. You can find some resources on this particular repository where you can do some inferencing on, images as well as videos. You can check out this repository that I have already shared with you. Gemma Cookbook is also a great resource for you to, learn more different models of the Gemma family. When no one asked me what is the full form of PaliGemma. So Gemma, of course, everyone understands it's a Gemma language decoder, but the Pali stands for this. So instead of Palm, right? Instead of using the Palm, which is Pathways language model, it was Pathways language image model. So that's where the Pali word came from, and the Gemma was the decoder model. So the thing is, I always, suggest or advise, if you are learning something, just go a step ahead and also understand something in depth, right? Instead of just simply calling an API, you can also try to dig further how these models were built. So Pali was built using vision transformers, VIT, what we call it as, right? And without you explicitly training it for different sort of data sets, right? It's good enough to understand everything in zero shot. And few folks had questions about OCR. If you want to do some OCR on a very complicated images, right? For example, receipts or something like that, which has some structured or unstructured format or layouts, right? So you can also train this model, based on those data sets. So you can find some good resources on fine-tuning PaliGemma 2, available on RoboFlow. Okay. So this thing explains how you can create your own fine-tuned version of PaliGemma 2 on a receipt dataset, probably, right? So this will become your image, and this will become your text, which will become, which will go as a dataset. Okay, it's a JSON format where the key represents the entity in the image, and the value would be the corresponding value, and this model will perform better as compared to the pre-trained version of the PaliGemma 2 model, right? And you can also follow the Google AI Edge repository, or the library which is recently released by Google. So before this, you must have heard about TensorFlow and TensorFlow Lite. So TF Lite has been deprecated. Now it is no longer used. Instead of TF Lite, Google has rebranded it to Lite RT. So TF was TensorFlow, but no longer any of the companies use TensorFlow now in their backend. So every model weights that you see, right? If I go to Hugging Face, I'm telling all these small details because we somehow tend to miss on these, on these details. So if you see, okay, these safe tensors, all these thing, right? The .pt thing as well. You must have noticed some models have those .pt as the extension. Those, the PT stands for PyTorch. So since we are not using TensorFlow anymore, Lite RT came into the picture, okay, which replaced TensorFlow. It supports all kinds of backends: TensorFlow, PyTorch, JAX, and so on. And this was specifically built for on-device use cases. So if you're interested in learning how do you run a model on an Android or iOS or Linux and so on, or even on web as well as IoT devices like Raspberry Pi and so on, right? So feel free to check this out along with some sample applications to get started with. Uh, yeah, that's pretty much about this session, and feel free to reach out to me if you have any queries or questions. I'm open for any questions right now, but if you think that if you want to share some offline or after the session, feel free to reach out to me on LinkedIn. And if you want to share some of the works that you have built or you have been building so far, I'll be happy to see that.
If anyone has any doubts, they can ask Sir right now. Otherwise, you can contact him after the session via LinkedIn. Okay, so thank you so much, Nitin sir, for this incredibly insightful session. Today's walkthrough gave us a clear picture of how visual language models, especially Gemma 3 and PaliGemma 2, can be used to build powerful on-device AI experiences. This live demo really showed how accessible and practical this technology has become nowadays. And thank you everyone who joined us and stayed engaged throughout this session. We hope we sparked some new ideas and curiosity. You can connect with the whole team via these QR codes, and Nitin sir has also shared his socials with you. And once again, I would like to thank Nitin sir for his time and sharing his expertise with us. Um, let's have a great day ahead and stay tuned and stay engaged. Thank you.
Thank you so much.
Thank you, sir.